The world of quantum mechanics is strange and fascinating. It operates on principles that are vastly different from the classical physics we are accustomed to. It challenges our everyday intuitions and forces us to rethink our understanding of reality. For instance, particles can exist in a state of superposition, meaning they can be in two places at once or in multiple states simultaneously. Another mind-boggling phenomenon is quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, regardless of the distance separating them. The act of observing a quantum system can fundamentally alter its state, a concept famously illustrated by Schrödinger's cat thought experiment. For centuries, physicists relied on classical mechanics, a framework established by pioneers like Isaac Newton. Newtonian physics provided a comprehensive explanation for the motion of planets, stars, and other celestial bodies. It worked perfectly for large, macroscopic objects, offering predictability and precision. However, as scientists delved deeper into the microscopic world of atoms and subatomic particles, they encountered phenomena that defied classical explanation. This led to the groundbreaking development of quantum mechanics in the early 20th century, a revolutionary theoretical framework. Quantum mechanics describes the behavior of matter and energy at the atomic and subatomic levels, revealing a world that is both perplexing and awe-inspiring. It is a mind-bending theory that has revolutionized our understanding of the universe, opening up new possibilities and questions about the nature of reality itself. One of the most bizarre aspects of quantum mechanics is the idea that particles can exist in multiple states at once. This is known as superposition. A particle can be in two places simultaneously. It can spin in two directions at the same time. It can even be both a wave and a particle. This concept is completely alien to our everyday experience. In the macroscopic world, objects have definite properties. A ball is either red or blue. It cannot be both. It is either moving or stationary. It cannot be both. However, in the quantum world, things are different. Particles do not have definite properties until they are measured. Before measurement, they exist in a superposition of states. The famous double-slit experiment demonstrates the principle of superposition, a fundamental concept in quantum mechanics. This experiment has puzzled scientists and intrigued physicists for decades. In this experiment, electrons are fired at a barrier with two slits. These electrons are tiny subatomic particles that we usually think of as the building blocks of matter. Behind the barrier is a screen that detects where the electrons land. This screen is crucial for observing the behavior of the electrons as they pass through the slits. If electrons behave like tiny balls, we would expect to see two bright bands on the screen, corresponding to the two slits. This is because each electron would pass through one slit or the other, creating two distinct impact zones. However, this is not what we observe. The results are far more intriguing and unexpected, challenging our classical understanding of particles. Instead, we see an interference pattern with multiple bright and dark bands. This pattern is similar to what we would expect if we were dealing with waves, not particles. This interference pattern is evidence that the electrons are behaving like waves. Waves can interfere with each other, creating regions of constructive and destructive interference. Waves interfere with each other, creating regions of high and low amplitude. This is why we see bright and dark bands on the screen, as the wave-like electrons create an interference pattern. This is why we see bright and dark bands on the screen. The electrons, behaving like waves, interfere with each other, creating this distinctive pattern. The truly mind-boggling aspect of this experiment is that the interference pattern persists, even when we fire the electrons one at a time. This suggests that each electron is not just a simple particle. This means that each electron is somehow interfering with itself. It behaves as though it is passing through both slits simultaneously, a phenomenon that defies our classical intuition. It is as if the electron is passing through both slits simultaneously. This remarkable behavior is a direct demonstration of the principle of superposition, where a particle exists in multiple states at once. The double-slit experiment, along with countless other experiments, has confirmed the validity of quantum mechanics. Particles can indeed exist in multiple states at once. They can interfere with themselves. The act of observation can determine the outcome of a quantum event. These discoveries have profound implications for our understanding of reality. They suggest that the universe is not as deterministic as we once thought. At the quantum level, there is an inherent randomness and uncertainty. Section 5. The many worlds interpretation. One interpretation of quantum mechanics that attempts to explain these strange phenomena is the many worlds interpretation. This interpretation suggests that every time a quantum measurement is made, the universe splits into multiple branches. Each branch represents a different possible outcome of the measurement. For example, in the double-slit experiment, the many worlds interpretation would say that the universe splits into two branches when an electron encounters the slits. In one branch, the electron goes through the left slit. In the other branch, it goes through the right slit. Both branches are equally real, but we only observe one of them. Section 6. Quantum tunneling, walking through walls. Another mind-bending phenomenon in quantum mechanics is quantum tunneling. In classical physics, an object needs a certain amount of energy to overcome a barrier. For example, a ball needs enough energy to roll over a hill. However, in the quantum world, particles can tunnel through barriers, even if they don't have enough energy to overcome them. This is because the wave function of a particle can extend beyond the barrier. There is a small probability that the particle will be found on the other side of the barrier, even though it didn't have enough energy to get there classically. Quantum tunneling has important implications for a variety of technologies, including transistors, flash memory, and nuclear fusion. Section 7. Quantum entanglement, spooky action at a distance. Perhaps the most mind-boggling phenomenon in quantum mechanics is quantum entanglement. This occurs when two particles become linked, even when separated by vast distances. They share the same fate, no matter how far apart they are. When we measure the state of one entangled particle, we instantly know the state of the other particle, even if it is light years away. This seems to violate the principle of locality, which states that an object can only be influenced by its immediate surroundings. Einstein famously called entanglement spooky action at a distance. He was deeply troubled by it, as it seemed to contradict his theory of special relativity. However, numerous experiments have confirmed the existence of entanglement. Section 8. Quantum mechanics in our everyday lives. While quantum mechanics may seem like a strange and esoteric theory, it has very real implications for our everyday lives. Many of the technologies we rely on today, such as computers, smartphones, and lasers, are based on the principles of quantum mechanics. For example, transistors, the basic building blocks of computers, rely on quantum tunneling to function. Lasers rely on the quantum properties of light to produce their intense beams. And magnetic resonance imaging, or MRI, a common medical imaging technique, exploits the quantum properties of atomic nuclei. Section 9. Conclusion. The future is uncertain, and that's okay. Quantum mechanics has revolutionized our understanding of the universe. It has opened up new realms of possibilities and has challenged our conventional wisdom. It has shown us that the world is far stranger and more wonderful than we ever imagined. The mysteries of the cosmos are more profound than we could have ever dreamed. Particles can be in two places at once. This phenomenon, known as superposition, defies our everyday experiences and challenges our understanding of reality. Information can travel instantaneously across vast distances. This is due to a phenomenon called quantum entanglement, where particles become interconnected in such a way that the state of one instantly influences the state of another, no matter the distance. The act of observing a system can change its outcome. This is known as the observer effect, and it highlights the intricate relationship between the observer and the observed. The implications of quantum mechanics are still being explored. Researchers around the world are delving into these mysteries, seeking to understand the fundamental nature of reality. It is a rapidly evolving field with many unanswered questions. Each discovery leads to new questions, pushing the boundaries of our knowledge and understanding. However, one thing is for sure: quantum mechanics has forever changed our view of reality. It has reshaped our understanding of the universe and our place within it. It has shown us that the universe is not as deterministic as we once thought. The classical view of a clockwork universe has given way to a more complex and dynamic understanding. At the quantum level, there is an inherent randomness and uncertainty, and that is okay. This randomness is not a flaw but a fundamental feature of the universe. In fact, it is what makes the universe so interesting. The unpredictability and randomness give rise to the rich tapestry of phenomena we observe. The uncertainty at the heart of quantum mechanics is what allows for the incredible diversity and complexity we see around us. It is this very uncertainty that makes life and the universe so fascinating and full of potential.